Hello students, 2023 electronics essay question. This is actually 2023-24 in between electronics essay questions. We have done 2024 electronics essay question. You must have watched it. If you find this question is difficult, yes, this is for you. I'll guide you through step-by-step method just to go to the solution. It won't be that hard, but you will learn quite a lot in this question. Let's go.
Students, at the first part of the question, they're asking us to give some explanations. What is the reason for formation of a depletion region in the diode? So you have to explain what is happening there. So it's a bit of a theory types question. Right. Then moving into the second part, the diode, we can see a Zener diode and a transistor as well. So using these electronics devices, we have this question. And moving into the third part C, we have an operational amplifier, and it's in closed loop. Hope you can see it, and you have to have this clear understanding of operational amplifiers and closed loop method. And from that we get couple of questions. We have 7 questions actually. So that is the structure of this question. So let's dive into the answers now. In the first part of the question, they are asking us the reason for the PN junction, the depletion layer. Students, the depletion layer forms, here we have positive, the holes, and here we have negatives, the negative charge. So when these two semiconductors combine, what happens is the majority carriers, inside we have majority carriers is electrons, and it moves towards this direction, and these will move this direction. Basically, when negative and positive are connected, positive will move to negative side, negative will move to the other side. This happens. So here at a certain point, here will be more negative charges, here there will be more positive charges. Right? We have to use the proper words. In the question they're asking why the depletion layer is formed, so you have to use the proper words. Moving certain charge from this side to the other side, you have to use the word diffusion. So diffusion of majority carriers towards the other side and recombination of it will form the PN charge. So here we have negative charges, here we have hope. Some of will cancel off, neutralize, and some will stay here like this. And now basically what happens here, students, there will be an electric field towards this direction, right? But now we need to send current, say, in this direction. This is the direction where it's forward bias. You know that, right? So then when we need to move current from this direction to this direction, there will be an opposite force, opposite electric field towards this direction. So to break that barrier, we need to apply a certain potential. So for silicon it's 0.7 volt, and for germanium it's 0.3. This is what basically happens in depletion layer. It's depleted. Majority carriers are depleted. So that's why it is called a depletion layer. So you don't have to know everything, but you should know everything for sure, but you don't have to write everything. You have to write the proper words. The diffusion of majority carriers and recombination of it will form a depletion layer, depleted. So they get neutralized. That must be your answer. Right. In the third question, they're asking us why there's a lead current even in reverse bias. So in reverse bias, students, remember, even in N-type semiconductors, there can be minority carriers, positive holes in this side and negative in this side. In the depletion layer, certain amount of these charges can lead towards its positive. So it's in negative form, depletion layer is greater now, but still positive charge can move to this side because it's positive, here positive. If there is positive charge, it can move to this side. So there's a certain small amount of, we call it minority carriers here in this side. So it can diffuse to the other side. So you have to write diffusion of minority carriers from one side to the other side. That creates weak small current. That you have to write diffusion. Again, the word you have to write diffusion of minority carriers, the other term. Students, now we are in the B part, the second part of the question. We have three parts, part A, part B and part C. Now we are at part B. Right. I hope you have tried this question before just looking at this explanation. I'm inviting you to do the question, students. You have to practice it first. You have to try it first. Right. Let's get into the question now. Initially, they're asking what is the purpose of the Zener diode in the circuit. Right. Students, Zener diode is actually being used to control the potential difference. The potential difference across it. So if it's connected with another resistor, let's say in a certain circuit, it will control the potential difference at a certain value that is given. Say now we are using a 6 volt potential difference reverse bias voltage Zener diode. This Zener diode can hold the same potential across this R resistor. Whatever the potential that comes over here, that must be greater than 6. Let's say 10 volt come over here. This resistor will get only 6 volt. There's another resistor that will get 4. Right? Whatever the irrespective of the value of these are, the potential difference across, let's say, these 2 points A and B, it will not change. So that's the purpose of using a Zener diode. It can control the potential difference at a fixed value. Right? So in our syllabus, in certain types of theories, actually this is being used. You must have noticed it in half wave regulator and at the full wave regulator questions, the circuit diagrams, these Zener diode is being used. So if you have practiced your theories, you know this, right? So basically they're asking what's the purpose of using Zener diode here. So it's regulating the potential difference across the given terminals. That's it. If you write that, you get the answer correct. Right. Moving into the second part. If the Zener diode potential Vz, write down an expression for Re in terms of IE Vz, i.e. the current through this, and by using Vz, okay, and VBE. Here students, they are asking, I'm writing it here, to write an expression for Re. So the current through Re is given. So basically what we have to do is we have to apply V equals IR, right, to this. So let's apply V equals IR. So what's the potential difference across Re? Potential here, it is Vz, right? So there's potential at B terminal here, that will be Vz as well, right? If here it's Vz, potential here, that of course you have to think. The current comes from B to E, forward bias. So the potential B is greater than potential E, and the potential difference VBE is given as 0.7. So here I'm just writing VBE. So see, now the potential here is 0.7 volt. So if the potential here, whatever the value is, it is, we have to subtract it from 0.7, we get the potential. So potential at this point, it is Vz minus VB. Right. Now we have the potential, here it's 0. So the potential difference will be Vz minus VBE. Current, let's say it is. Then we need to divide it by I, the current through it, that's IE. Here we go, we get RE value. That's the expression they are looking for, and that's our answer. And then we have to apply the values, I think, the next part of the question. Let's read it. If the circuit needs to produce a constant current of ID, what's ID? Current through here. So normally in the normal circuit, actually we call this part IE. I hope you remember stuff like this. So here it's IE, here it's IC, but here they are giving us it's ID because of the diode. ID equals 20 milliamperes. Calculate a suitable value for RE. Take VZ at 5.7. Write down an assumption you would make during the calculation of with regard to ID. Right. Students, this circuit diagram is voltage divider method. When biasing a transistor, there are two methods to bias it. You should know these things. First one, the resistor method, base resistor method. There is only one resistor, we don't have anything like this here. Base resistor method. And the other one is voltage divider method that is being used here. Right. So in the voltage divider method, we make an assumption when we do the question. So if I practice students questions like this, you know the assumption. So assumption what we do here is we get here is ID or the IC value approximately equal to IE value. Actually we get from this, students. I hope you know the equation I equals IC plus IB. Students, IB is a very small value compared with IC and IB. So in many cases we can assume IE equals IC. Normally in a question actually we get this point only if beta value is not given. Now what is beta? Beta is the current gain IC over IB. Students, you should know this. So if IB value is not given, and if you cannot find IB from any method, then only you can make this assumption. So here beta value is not given, you cannot find IB. So you cannot add these two and find I. So you can assume IC equals ID. So that's the assumption you're gonna make. So the assumption you're gonna make, ID equals to I. Right. So we are applying to the very same equation. Now the current IE is 20 milliamperes. 20, right? Yeah, 20 milliamperes. I'm going to write here. I hope you can see it. So VZ 5.7 volt minus VBE 0.7 volt, IE 20 milliamperes, 20 into 10 to the power minus 3, and we get RE. Right. Let's do the simplification over here. Right. Okay. 5.7 minus 0.7, that will be 5, and divided by actually 10 to the minus 3, that will I can send up, and we have 20 here. So I can multiply this by 5 and this by 5. This is how I might simplify. You can do whatever the method that's comfortable with you. Right? So it's 25 over 100 into 10 to the power 3, 0.25 into 10 to the power 3, 250 ohms. Students, we have the answer for the last part, right? Yeah, part 4. Part 3, we have another, right? 250, that's our answer. Right, 4, show that the circuit works as a constant current source if VCC equals 12 volts and VZ 5.7, the forward bias potential drop across the silicon diode is 0.7. To supply a constant current, you should know this actually. The transistor must be active region. Say now IC over IB equals to beta. In active region, it's proportional, directly proportional. You change IB and IC will be varied. So if you make IB constant, IB is constant, right? So you have to make sure IB is constant anyway, and you have to make sure the transistor is in active region. So if VCC, supply voltage is 12 here, potential drop 5.7 here, and here the potential will be 5.7. So here potential will be 5. Okay. And potential here Right. Again, back to theories. To show that any transistor operates in active region, let's take a look at let's have a look at here the regions. These are the regions: cutoff region, active region, and saturated region. So I'm going to use this graph here. I think I have to make a small adjustment. Right. Change it. IB and IC, this is called transfer characteristic curve. If you don't know these things, note it down, students. Go through with your theory notes and check it again. Right. It varies like this. Transfer characteristic curve. Goes like this. It goes like this. This is saturated region. VCE equals 0. Saturated region. VC equals VCC. In active region, the VCE value is in between 0 and supply. So to show the transistor operates in active region, you have to show VCE, this potential difference, CE potential difference must be in between 12 and 0. Any value. It cannot be 0, it cannot be 12, something like that. Right. Now we know the potential here. VE point is 5. So we need to find the potential at C. It's a junction diode. It will keep only 0.7 volt at forward bias. So the potential here, it will be 12 minus 0.7 is 11.3. So the difference 11.35 minus 11.3 minus 5 is 6.3. So 6.3 students in between 0 and 12. That you have to write. 6.3 is in between 0 and 12. So the transistor operates in active region. So when the transistor operates in active region, the circuit can be used as a constant current supply. So the circuit can supply constant current. That of course you have to write. Students, go through with the marking schemes, as I have mentioned a couple of times. Go through the marking scheme. Then only you can see the way they have given the answers, the way they are expecting the answer. Right? We have come to the end of the second part, B part. So now we are moving to the part C, where we get an operational amplifier. C part of the question. So first question. What is operational amplifier configuration shown in the figure 2? Yeah. Students, it's an easy question. I hope you must have done many questions from this side. If you cannot tell the type of configuration of this, you haven't studied, right? Right, students, there are basically two types, closed loop and open loop. So this is basically closed loop. How do you recognize closed loop? There's a direct connection between output and input here and feedback connected. So when it's connected, it's closed loop. That's not enough. If this is closed loop and the input signal here is given to the negative terminal, inverting terminal. So it's closed loop, inverting amplifier, or inverting configuration. You can write answer that way. Moving into part 2. The golden rule. Right. Students, if you have practiced past papers, you must have come across this. In past papers, they have directly asked from you, what are the golden rules of operational amplifier? So if you have gone through with the theories, you know the reason for golden rules. Actually here they have given the golden rule. So they are asking something inside of it. Let's read it. The golden rule 1 states that no current flows into the input terminal. What is the reason for this? Okay, no current flows. Actually, in an ideal operational amplifier, the input resistance is very high. That's what you have to write. The input resistance of an operational amplifier is very high. So no current can enter through the operational amplifier. Input resistance is very high. That's the key word there. And moving into the second part, the golden rule 2. It states that the potential difference between the input terminals of an operational amplifier is 0. Right. Students, recall to the open loop condition. In open loop situation, if you can remember the equation, capital A VA minus VB is equal to V. Right? A value here, it's closer to 10 to the power 5 in most cases. So it's a very high value open loop gain. So even if there is a very small potential difference between these two terminals, it will increase to a greater value, right? So in closed loop, what actually happens here, we need to make sure the potential difference is 0 of these two terminals. Even if there's a small change, we will be getting a very high output. So what actually happens is, once this is negative 0, the negative feedback will automatically cancel off this any potential here, and it will create a virtual 0 here. So that's how you make it 0. You don't have to explain all these things. What you have to tell is by giving a negative feedback, the resistance, the potential difference, the potential difference becomes 0 by using a negative feedback from output voltage. That's what you have to write, students. So this is a clear indicator that shows that you have to read theories and understand theories other than doing the questions, getting answers and all that stuff, doing the calculations and all that. So you have to understand your theory. So students, how do you understand your theories? Basically, it's not about listening to some video or anything. You have to read. So I hope you must have got a theory tube. So you read the theory tube. So once you read the theory tube, you'll understand the concepts. So rather than you have to do questions, you have to listen to videos and whatever it is there, you have to go to classes. That's true. But learn some theories. What does it mean by small things, small steps, like we discussed it. You have to, if you have practiced those things, then you can easily write down those theory types answers. If you are not good with theory types questions, basically when you are doing MCQ paper, you will find it really difficult to do statement type questions. So if you find doing statement type questions is really hard, that means you are not good with your small theory. In part C, fourth part, right? Applying the two golden rules, derive an expression for output voltage V0 in terms of small input V1, Vi, R1 and R. Right. Student, I'm telling you this again. If you have practiced your theories, writing down this is very easy thing. Right? You have to practice your theories. Right. So how do you prove V0, right? V0, right? Yeah, V0 in terms of these. Right. Potential here is 0. So the potential here, it has to be 0. So V out divided by V in equal gain, right? What are they asking? Yeah, apply to golden rule, expression for output V0 in terms of small Vi. Or, okay. So the connection between V out and V in, that's what they're asking. Current here, say this current flows this way, it won't go in, so it moves in this direction. So these two currents are equal, right? So current in this path and this path are equal. The potential difference in this path is V0 minus 0. So V0 minus 0 divided by R2, that is that in others? R2, R2 is that, yeah, R2. That's the current in this path. It must be equal to this path current. Potential difference in this path, 0 minus V1, 0 is greater. 0, because it moves from this direction to this direction. Hope you can see it. 0 minus V1 divided by R1. Right. Going through the simplification, V0 over R2 equals minus V1 over R1. So V0 equals minus R2 over R1 into V1. You should remember this equation, right? But anyway, you have to write. If you can write in this method, actually that's good. Or either if you get this, if you have written this, you will be getting marks. Students, study your theories, right? The next part.
if small input potential between 0 and 0.7, so input value, Vi value can be 0, 0.7, and the gain, it has to be in between 0 and 3.5. We don't have to worry about 0, we should increase the 0.7 up to 3.5. So you can see the value 3.5 divided by 0.7, that will be 5. So they are asking, determine the voltage gain of the operation amplifier. It's really hard, right? So what we have to do? We have to divide output voltage by input voltage. Output maximum 3.5, input maximum 0.7, we get 5. That's the answer. Right. Then the small input voltage at 0.7 linearly drops with temperature by 2 millivolt per Celsius. Calculate the output voltage of operational amplifier corresponding to 10 degrees Celsius increase in temperature in VL. So initially it's 0.7, 2 millivolt per 1 degree Celsius. So 10 is 20 millivolt. In volt it's 0.02, right? Yeah. So 0.7 minus 0.02. What's the value I'm getting? It's 0.68, right? Yeah, 0.68. That's the input voltage, 0.68. So 0.68 multiplied by 5. 44, 3, 4. So 3.4 volt. That's your answer. These are simple calculations, right? The last one, 7. Students, actually this question I see, they are asking from us lots of theories. We have to explain theories. Students, actually we cannot remember theories. We have to do questions. When you do questions, you come across theory questions, so you answer them, or you read in this kind of a video, you'll get to know certain things. Remember these things, right? Okay. The voltage gain of the operational amplifier circuit can be set by choosing R1 and R2 values in ohm range, in small values. Here, to get this but yeah, the 5 voltage gain, you can use these two values. This is the gain, right? R2 over R1. This is the gain. So R2 can be 100 and R1 could be 20. So 100 divided by 20, that's 5. 1000 divided by 200, something like that. But they ask me why we should use kilo ohm range. Basically, it's the reason input resistance of this circuit must be very high. There's a word input resistance, yes, but you can write the word impedance as well, and input impedance or input resistance, whatever. Even if you write resistance, that is correct. So input resistance of the circuit must be higher so that the kilo ohms range resistance are being used. You know, the input resistance must be really high for an operational amplifier. That's a golden rule even. So we are using high resistance to make the input resistance is higher. So that's the answer, right? And that's wraps up our 2023 electronics essay solution. Right, students, if you find this is really helpful, or whatever it is helpful, give it a thumbs up and hit the subscribe button. If you need more these type of solutions, tutorials, and if you have any comments, yes, any suggestions, please feel free to let me know. Right, students, study together, win together. Cheers.